More.
The Lovell telescope is now 45 years old, the first great radio telescope and still the most famous in the world. Good evening. I'm at Jodrell Bank in Cheshire at the great Radio Astronomy Observatory with the 250-foot Lovell telescope. And you know, it's amazing to think now that only a few months ago, this entire observatory was under threat. Well, I'm glad to say that threat has now been averted, and the telescope is not only operational again, but is now being upgraded. Andrew Ryan, director of Jodrell Bank, was naturally at the heart of the campaign to save it.
2 years ago, indeed, the observatory was under threat. We, at that time, looked to the possibility of having to close down the large telescope, and the second main facility we have here, the Merlin National Facility, was also in dire need of an upgrade. Since then, we've received a grant of about £2.5 million from the government to upgrade the big telescope by resurfacing it, giving it a much more accurate surface, and also providing a new control system. This should give it a lifetime of 15, 20 or even more years with a much greater performance than it has now.
Now, radio astronomy is quite different from ordinary astronomy, and you certainly can't look through a radio telescope. Light is a wave motion, and the colour of light depends on the wavelength. Blue is short wavelength, red is long. If the wavelength is longer than red, you can't see the radiation. Have microwaves and then radio waves, and these are connected with radio telescopes, many of which are in the form of large dishes. Now, radio astronomy began in the 1930s, but didn't become really important until after the war. And the first great radio telescope was set up here at Jodrell Bank, largely on the initiative of Sir Bernard Lovell.
The reason I had the idea of a big telescope is that the sensitivity of the original set, that is the army equipment, turned out to be entirely inappropriate for what I was trying to do. And the calculations which Patrick Black and I had made during the war under air attacks turned out to have missed out an important damping factor. And the only way of recovering that was to build a very large aerial. And so I moved over into another field which we borrowed from the farmer then, and began building large arrays.
And finally, we had the 250-foot, now the Lovell telescope. And I think a bit of luck came along then for funding, and that, of course, was working with the Russians and the first satellite.
Indeed. I mean, that's why we're here today, in fact, because I had run into enormous troubles. We'd been investigated by the Public Accounts Committee. You see, nobody had ever built anything like this before. And we were being pilloried by the press, and then the Russians launched Sputnik 1. Well, the Sputnik itself was easy to pick up because it was transmitting, but the launching rocket was a different matter. It was, in fact, the first intercontinental ballistic missile which carried the rocket. Well, to my amazement, it turned out that we had the only instrument in the Western world which was capable of detecting the rocket by radar. And we did so, and really that saved us. Our association with Sputniks and the American space program raised a lot of publicity, but in fact, it never occupied more than about 10% of the operational time of the telescope. And quite soon, discoveries of quite considerable importance for astronomy began to roll out of the telescope, particularly the measurement of the angular diameter of some of the distant objects, which were then identified as radio galaxies. And that led in the early 1960s to the discovery of the quasars, one of the hitherto recognized objects in the universe.
I well remember the 30th anniversary. 5787 was painted on the dish, and it was my job to help keep Sir Bernard out of the way until it was unveiled. I'm glad to say we succeeded. Of course, there are always problems, and one man deeply involved is another regular visitor of our program, Ian Morrison. Well, Ian, the Lovell telescope is now being upgraded, and it did need it.
Very much so, Patrick. It was extensively rebuilt in 1971 and given a new surface. after 30 years, that surface had become very badly corroded. So a major part of the upgrade is to replace it with a new surface made of galvanized steel, which shouldn't rust. Each panel of the telescope surface, there are about 360 of them, is now much smoother than it was before, and that helps. But as well as that, every panel can be adjusted. And we now have a holographic method that enables us to make a map of the surface showing which panels are too high, which are too low, away from the perfect parabolic shape.
When you have your telescope upgraded, what are the immediate prospects?
Well, we will be able to use it at much higher frequencies than we've been able to in the past, by something like a factor of 3 or 4. This will enable us to study new phenomena. For instance, we'll be able to study methanol in the universe. Methanol has been shown to be a very powerful tracer of the regions of star formation in the universe. And so we should be able to discover regions of star formation with out to very large distances into the universe, and to study all the processes that go on there. At the moment, it's very difficult to see such regions because they're normally shrouded in dust and gas that prevents you seeing into them, but radio waves enable us to penetrate those regions.
Over the years, many pulsars have been discovered from Jodrell Bank. Pulsars are the remnants of stars that have exploded and destroyed themselves, leaving behind small, quickly spinning remnants. The director of Jodrell Bank, Andrew Lyon, is very interested in pulsars. And for the Sky at Night, he and his colleague, Mike Kramer, have created some special Sky at Night music. Let's listen in to a pulsar.
Yes, well, pulsars emit radio waves which travel through space, and just as if we were listening to a wireless set or an ordinary radio, we can hear signals coming from the stars. And so the signal from one of these pulsars may sound like this. And this is a recording of a pulsar which is rotating, in fact, with a period of 0.714519 seconds. And every time this pulsar rotates, just like a lighthouse beam, when the beam crosses the line of sight to the Earth or crosses the Earth, we get a pulse of radio emission, which you can hear there.
The others are faster than that. What about the Crab Nebula?
Indeed, the most well-known pulsar is in the Crab Nebula, and this sounds much faster. This is rotating at 30 times a second. It's like a pneumatic drill.
It is indeed. Really, the music of the spheres.
One of the most spectacular discoveries was the first pulsar in a globular cluster. Since then, in fact, we've found no fewer than 20 millisecond pulsars in the globular cluster 47 Tucani. Now, these millisecond pulsars are pulsars which are rotating even more rapidly than those in the Crab pulsar. The fastest rotates about 600 or 700 times a second, and all these pulsars in 47 Tucani are rotating all several hundred times a second.
47 Tucani being a globular cluster too far south to be seen from here, and about 17,000 light years away. Some people still confuse pulsars with quasars, and quasars are very different. They're millions of light years away.
Yes. Pulsars are objects of stellar size, the same sort of mass as the Sun, whereas quasars are on the scale of a galaxy. They will often weigh as much as a million or many millions of times the mass of the Sun, and are black holes. And they radiate copious quantities of radio emission, and we can see them well across the universe.
We've shown a picture of the globular cluster 47 Tucani, containing around 1 million stars and 17,000 light years away. Now in imagination, let's go inside it. There are the stars, and there are the pulsars whirling round. Actually, of course, they do so much more slowly than that. And now imagine we can hear their notes, separately first, and then working up to, all together, a gigantic cosmic crescendo, a real cosmic chorus. The Lovell telescope isn't the only large radio telescope here, but also the Mark II. And these two, together with 5 others, make up what's called the Merlin Network, which the farthest flung is over at Cambridge. So let's have a look at the other 5 telescopes of Merlin.
Merlin is an acronym for Multi-Element Radio-Linked Interferometer Network. As the acronym suggests, it is an interferometer, which effectively is a radio camera. And we use Merlin to take radio pictures of objects in the sky throughout the universe.
What exactly is it and how does it work?
Each telescope receives the signals from a radio source, and those signals are then transmitted back to Jodrell Bank using microwave links. The signals are combined in a special purpose computer we call a correlator. They're processed by the astronomers to produce the radio images that are familiar to many people.
Well, could we see and hear about some of the results so far?
We can discuss maybe M82, which is a very familiar object to many of your viewers. It's also a strong radio source.
It's a galaxy, of course, quite near the large M81, both quite easily seen in small telescopes.
Absolutely, yes. I mean, it's 3 megaparsecs away. If you look in the radio, you look actually through all the dust that obscures the center of the galaxy. But if we look through the dust with Merlin, we make a radio image of the emission in the center of M82. We see a surprising thing. There are about 50 very bright, compact sources in the center of M82. These are actually supernova remnants. And we can show that there's a lot of star formation in M82. There's also a lot of star death. And we're expecting to see a supernova about every 30 years. So since the most recent one went off in 1960, we're actually overdue for another one.
I hope you're lucky. Well, the Hubble Deep Field, the Hubble telescope, looking right out into space as far as you can, imaging things more than 10,000 million light years away. I imagine Merlin has studied that field too.
Yes, in fact, many observatories around the world have tackled the Hubble Deep Field. It was a fascinating project. It's a very small area of sky. In fact, the whole deep field is equivalent to a grain of sand held at arm's length in area. But within that, the Hubble Space Telescope saw thousands of galaxies. Merlin observed it for about 18 days, and within that same region found about 90 galaxies. But the crucial thing that Merlin supplied, which enabled all the observations from all of the other observatories to be tied together in position, was what we call the astrometry. That's measuring the absolute position of objects. Now, the Hubble is not very good at doing astrometry, but Merlin is superb. And so it was able to help all the other observatories line their images up. We were able to show that a lot of these galaxies are starburst galaxies, that is, galaxies undergoing massive bursts of star formation.
Like M82?
Like M82. M82 is a nearby example. Those we're seeing in the Hubble Deep Field are more distant examples.
There have been other unexpected discoveries, such as gravitational lenses, first identified in 1979. And this is something of which Jodrell Bank can be very proud. One of the leading researchers here at Jodrell Bank is Professor Peter Wilkinson. Welcome to the Sky at Night, Peter.
Thank you, Patrick.
Now, gravitational lenses, what are they?
Well, even before Einstein, astronomers realized that light would be bent as it passed by a massive object in the universe, like a star or a galaxy. But it was Einstein who actually worked out the correct equation. For many years, people didn't think they'd be able to see this effect, bending of a light, because the effect is really rather small. But in 1979, an astronomical team led by Dennis Walsh at Jodrell Bank found the first gravitational lens, a double quasar, where the light had been bent by an intervening galaxy, just as we see here in this image, where here's the Earth and here's the galaxy in between us and a distant quasar, and light is bent around the quasar to form 2 images.
And there are other fascinating things too, things like rings, aren't there?
Indeed, yes. In fact, you can see this rather easily with a home-built gravitational lens, which we can see here. Yeah. I think it's an excellent effect.
Yes.
The bottom of a wine glass bends light in almost exactly the same way as a galaxy or a star does distant light coming from a distant object. A piece of glass shaped, bending up like that, and then over and back, down like this. If you broke off the stem, heaven forfend,
Certainly.
And looked at it, you can see Einstein rings. I just happen to have a better one here.
No.
Just a piece of glass up in the middle, and back over again like that.
No.
Now, if you look at a piece of paper with a red blob in it and put the lens over it like that, you can see a beautiful Einstein ring. The light is bent around in a circle. So what was a blob becomes a ring. You can see that yourself.
So in fact, a galaxy behind another galaxy can be distorted into a ring.
Exactly, and we in fact see those in space.
Can I hold it some?
Yes. For example, here, one of the lenses we found in the big gravitational lens search we've done at Jodrell Bank, the most successful in the world, incidentally, we found 23 new lenses, is an object called 1938 plus 666, rather boring astronomical nomenclature, but nevertheless, down in the bottom left-hand side here, you see the radio contours, as if you had radio eyes. This is an image made with Merlin. See beautiful arcs.
Yes, indeed.
Now, really, you can see that arc is probably part of a circle. And if you go and look at that with the Hubble Space Telescope, you see a beautiful Einstein ring, where the ring is the light from the distant galaxy bent around in exactly the same way we saw here, and the blob in the middle, the bullseye, if you like, is the galaxy doing the lensing. So Einstein's prediction of 60 years ago and more is perfectly borne out.
What are the most important aspects of gravitational lens research?
Well, there are many different things you can do with the lenses. One interesting thing is to study the distortions. They're distorted into one pairs or triples or quads or even rings. And from studying those distortions, it's the only way where you can study how the matter is distributed in a distant galaxy. No other way can do that. But perhaps more interestingly at the moment, and very excitingly, are results on just counting the number of lenses. It tells us something about the properties of the universe, the geometry of the universe. And we're finding from our big surveys at Jodrell Bank that the universe is not just dominated by matter, stars, galaxies, not just dominated by dark matter, whatever that is, but dominated by something even more mysterious, so-called dark energy.
All right, Peter. What is dark energy?
Nobody knows, Patrick.
Well, looking back now over 50 years when you were starting, did you think you'd have got this far by now?
No, Patrick. Well, when the telescope came into operation, I had hoped it might be useful astronomically for 15 years. And the engineers turned to me and said, my dear fellow, you'll be lucky if it's still working in 15 years. It was such an unusual and relatively delicate structure. So naturally, I'm delighted that it's still there.
As you can see, we've come a very long way since Jodrell Bank really was a grassy bank with no radio telescopes. And the observatory is still very much in the forefront of astronomical research and will certainly remain so in the coming years. Meanwhile, don't forget our website, www.bbc.co.uk/space, CFAX, page 600. And so until next month, goodbye.